Video project, Peter Samouras's recording. The entirety of the video project's tasks began with picking the structure that we wished to analyze. I chose my veranda in my backyard because it always interested me to know how the loads were transferred through so little beams. The first stage consisted of me getting the measurements of the entire veranda and making sure that they were accurate for the other two tasks to come. Video project, task 2, required me to further analyze my veranda and come up with shear force and bending moment diagrams. In order to achieve this, I had to first find the internal forces, and to find the internal forces, I needed to find the reaction forces. To begin this process, I simplified my structure into a simply supported beam that was horizontal, and in doing so, I was able to solve for the reaction forces. This then enabled me to make a cut in my simply supported beam with distance x to find the internal shear force and bending moment equations, which could then be used to sketch the bending moment and shear force diagrams. These can be seen on screen. In addition, since my structure is perfectly symmetrical, analysis of only one half was required, as these graphs would be mimicked on the other half of the structure too. Using the information gathered in task 2, I was able to determine the slope and maximum deflection equations for the predetermined uniformly distributed load across my beam. Finding these equations was quite simple because all it required was the double integration of the bending moment equation that was found in task 2. This resulted in two equations with integration constants seen in my working out on the slide. In order to remove these constants, I applied a set of boundary conditions, and those were at each support, so at x equals 0 and x equals 2.6 for my structure, 2.06 meters, the deflection was equal to 0. With the computation of some simple algebra, I was able to determine these two equations seen on the side of the slide. Upon the determination of these equations, I was able to find the point where maximum deflection occurs, where the slope equals 0. Solving for the slope equaling 0, I found that the position was x equals 1.06 meters, which is perfectly in the center of my beam. Substituting this x value into the deflection equation will give us the maximum deflection, which was 0.0393 millimeters. When comparing this to the theoretical maximum deflection being 8.24 millimeters, the experimental deflection is 200 times smaller, and as such, the deflection present in my structure is a safe level deflection. In addition, the maximum shear force and bending moment values acquired from these diagrams in task 2 are used in the calculations of normal and shear stress. Stress state 1 occurs when the normal stress is at maximum and the shear force is equal to 0 on the edge of the beam. Since my beam is hollow, the moment of inertia is much smaller compared to if the beam was solid, and as a result, the normal stress is a much larger value. In addition, stress state 1 proves to be the critical point on the structure, as both the normal and shear stress in the plane are at maximum. The same process is to be undertaken for the second and third stress state. Second stress state occurs on the neutral axis of the beam, where the shear stress is at maximum and the normal stress is 0. These values determined in these calculations were both smaller than the ones determined at the critical point. Finally, stress state 3 is a combination of both shear and normal stresses being present in calculations. This occurs midway between the neutral axis and the edge of the beam. Again, like stress state 2, these values are not larger than those determined at the critical location of the beam, and as a result, do not need to be considered. In addition, in each of these stress states, the planes of failure and their orientation can be calculated. In stress state 1, the failure plane orientation for tension and compression, theta p, seen on the right side of the working out, is 0 degrees, and the failure orientation for shear stress, theta s, is 45 degrees. In stress state 2, these values are reversed. The failure plane orientation for tension and compression is 45 degrees, theta P, and the orientation of the failure plane for shear stress is 0 degrees, theta S. Finally, in stress state 3, the angles for the failure plane for tension and compression, theta P equals 2.43 degrees, and the failure plane of shear stress, theta S, equals negative 42.57 degrees, differ. This is the result of there being a combination of shear and normal stresses at this location in the beam.